What happens when one of the most engineered rivers on Earth begins to fail? What happens when snow that once buried the Rocky Mountains no longer arrives in the same volume, when reservoirs lose more water to heat and evaporation than entire cities consume, and when the river itself carries less water than the laws governing it assumed a century ago? Can a river carved over millions of years by tectonic uplift, canyon incision, sediment transport, and seasonal meltwater survive an age where climate systems are shifting faster than the basin can adapt? The crisis unfolding across the Colorado River Basin in 2026 is not simply a water management story. It is the collision between geology and modern civilization. Beneath every political fight over reservoirs and allocations lies a deeper physical system controlled by mountains, snowpack, sediment, groundwater recharge, atmospheric circulation, and the slow architecture of the North American continent itself. The Colorado River is now revealing what happens when those geological and climatic mechanisms begin operating outside the range that built the modern American Southwest. The river stretches roughly 1,450 miles, or about 2,330 kilometers, from the high Rocky Mountains of Colorado to the Gulf of California in Mexico. Over millions of years, it cut through uplifted plateaus and resistant rock layers, excavating the Grand Canyon and transporting enormous quantities of sediment toward the sea. Its existence depends on a delicate balance between elevation, precipitation, snow accumulation, melt timing, erosion, and evaporation. That balance is now shifting. Scientists monitoring the basin during 2026 describe conditions approaching a dangerous threshold. Snowpack in parts of Colorado and Utah reached record lows after a winter marked by persistent warmth and limited storm activity. Reservoirs including Lake Mead and Lake Powell remain critically depleted, with some projections suggesting Lake Powell could approach minimum hydropower levels if inflow continues declining. To understand why the river is under such stress, it is necessary to begin not with dams or cities, but with mountain building. The Colorado River system exists because the western interior of North America underwent immense tectonic deformation over tens of millions of years. During the Laramide orogeny, beginning roughly 70 million years ago, compressional tectonic forces uplifted the Rocky Mountains. Later extension and crustal thinning across the Basin and Range Province created alternating mountain ranges and valleys across Nevada, Arizona, Utah, and surrounding regions. The Colorado Plateau itself rose thousands of feet while remaining relatively intact structurally. That uplift fundamentally changed drainage patterns. Rivers gained steep gradients, increasing erosive energy. Water descending from the Rockies acquired enough force to carve deeply into sedimentary rock layers. The Grand Canyon itself represents the interaction between tectonic uplift and fluvial incision. As the plateau rose, the river cut downward faster, exposing rocks nearly 2 billion years old. But the Colorado River is not fed primarily by rainfall in the deserts it crosses. Most of its water originates in high elevations where winter storms deposit snow. The hydrology of the basin depends heavily on orographic precipitation. Moisture-laden air masses moving inland from the Pacific Ocean are forced upward by mountain ranges. As the air rises, it cools adiabatically, condensing moisture into snow. This snowpack acts as a natural reservoir, storing winter precipitation until spring and summer, warming gradually releases meltwater downstream. That delayed release mechanism is essential. Without snowpack, the river would become highly seasonal and unstable. Snow effectively smooths out hydrologic variability by storing water in frozen form for months. The timing of melt determines reservoir recharge, sediment transport, ecological productivity, and groundwater interaction throughout the basin. The problem emerging in 2026 is that rising temperatures are disrupting nearly every part of this mechanism simultaneously. Warmer winters increasingly cause precipitation to fall as rain instead of snow, especially at lower elevations. Snow that does accumulate melts earlier in the year due to elevated spring temperatures. Earlier melting changes runoff timing, causing peak flows to occur before reservoirs and agricultural systems are optimized to capture them. Hotter soils absorb larger fractions of meltwater before it ever reaches river channels. Scientists have observed that parched ground conditions following prolonged drought can consume enormous amounts of runoff through infiltration and evapotranspiration. The hydrologic mathematics become brutal very quickly. Even when total precipitation remains relatively stable, warmer conditions reduce runoff efficiency. A larger percentage of moisture returns to the atmosphere rather than entering streams. This phenomenon is sometimes called aridification rather than simple drought because it represents a long-term shift toward a drier equilibrium state. Recent reports warn that inflows into Lake Powell during 2026 may become the lowest since the reservoir began filling during the 1960s. Some forecasts suggested spring runoff could fall to only a small fraction of historical averages. Lake Powell and Lake Mead themselves reveal another geological reality often overlooked in public discussions. Reservoirs are not passive storage containers. They are dynamic, evaporative systems embedded within desert climates. Lake Mead sits behind Hoover Dam in a region where summer temperatures routinely exceed 110 degrees Fahrenheit, or about 43 degrees Celsius. Lake Powell occupies similarly arid terrain upstream. When enormous artificial lakes are placed in hot desert basins, evaporation becomes a major hydrologic loss mechanism. Vast surface areas exposed to intense solar radiation transfer immense quantities of water vapor into the atmosphere. Evaporation from the Colorado River system now removes millions of acre-feet over time. Climate warming intensifies this process because warmer air can hold more moisture. Increased vapor pressure deficits accelerate evaporative demand across reservoirs, soils, and vegetation alike. The geological setting amplifies the vulnerability. Much of the basin consists of porous sedimentary formations and fractured rock terrains where water infiltration can disappear underground. While groundwater recharge is beneficial in some contexts, overdrawn aquifers throughout the Southwest increasingly disconnect surface water from subsurface reserves. In some areas, groundwater extraction exceeds recharge rates accumulated over thousands of years. The river therefore faces a compound crisis driven by interconnected physical mechanisms. Reduced snowpack decreases runoff. Earlier melt shifts timing. Hotter soils absorb more moisture. Reservoir evaporation increases. Groundwater depletion alters hydrologic connectivity. Meanwhile, demand remains extraordinarily high. What makes the Colorado River especially vulnerable is that its legal allocation system was designed during an unusually wet climatic period. The 1922 Colorado River Compact divided water between upper basin and lower basin states based on flow estimates now understood to have been overly optimistic. Modern reconstructions using tree rings and paleoclimate evidence show that 20th century flows were abnormally generous compared with longer-term averages. The geology of the basin preserves evidence of ancient megadroughts long before modern civilization existed in the region. Sediment cores, lake deposits, and tree ring chronologies reveal prolonged dry intervals lasting decades. These paleoclimate records demonstrate that the river naturally experiences enormous variability driven by ocean-atmosphere oscillations and long-term climatic shifts. Today, those natural oscillations are interacting with anthropogenic warming. One of the major atmospheric mechanisms influencing the basin involves the position and behavior of the jet stream across the North Pacific and western North America. Storm tracks delivering winter moisture to the Rockies depend on large-scale pressure gradients and sea surface temperature patterns. Persistent ridging over the western United States can deflect storms northward, reducing snowfall dramatically. At the same time, warming oceans influence atmospheric moisture transport. The atmosphere may carry more moisture overall, but precipitation distribution becomes more erratic. Some storms become more intense while intervening dry periods lengthen. The result is increasing hydrologic volatility rather than stable replenishment. This matters enormously for erosion and sediment transport. Rivers depend not only on average discharge, but also on the frequency and intensity of peak flows. Reduced spring runoff weakens the river's capacity to move sediment downstream. Dams already trap much of the sediment load that historically rebuilt floodplains and delta systems. Reduced sediment transport alters channel morphology, destabilizes habitats, and changes thermal conditions within the river. The Colorado River Delta in Mexico illustrates the extreme downstream consequences of upstream alteration. Historically, the river emptied into the Gulf of California through a sprawling delta ecosystem rich in wetlands and biodiversity. Today, the river often fails to reach the sea at all. Diversions, reservoirs, and declining flows have transformed much of the delta into dry terrain. From a geological perspective, this represents a major interruption in sedimentary processes that operated for thousands of years. Deltas exist because rivers continuously deposit sediment at their mouths. When flow weakens and sediment delivery collapses, deltaic systems degrade rapidly. The river is also increasingly trapped in what hydrologists call a deficit cycle. Reservoir levels decline because inflow is insufficient to match withdrawals and evaporative losses. Lower reservoir elevations expose larger proportions of shallow shoreline relative to volume, sometimes increasing evaporative vulnerability further. Reduced water depth also affects thermal stratification and water quality. Lake Powell now hovers dangerously close to levels that threaten hydropower production during severe shortage scenarios. Federal agencies have already discussed emergency releases from upstream reservoirs to stabilize water elevations. Hydropower itself depends on gravitational potential energy. The higher the water column above dam turbines, the greater the hydraulic head available for electricity generation. As reservoir levels fall, turbine efficiency declines. Eventually, water elevations can become too low for normal operations. This introduces another geological factor: topographic dependency. Dams across the Colorado system were engineered assuming relatively stable long-term storage elevations. Those assumptions now collide with climatic conditions outside historical operational ranges. Even the chemistry of the river changes under prolonged drought stress. Lower flows concentrate dissolved salts and minerals. Salinity naturally increases downstream as water evaporates and interacts with rock formations. Reduced discharge means less dilution. Elevated salinity damages agriculture and ecosystems while complicating municipal water treatment. The Colorado River Basin crosses extensive sedimentary terrains containing soluble minerals deposited during ancient marine and evaporitic episodes. Water flowing through these formations naturally acquires dissolved ions. Under diminished flow conditions, concentration effects intensify. Meanwhile, vegetation across the basin responds dynamically to warming and drying. Forest stress in headwater regions increases susceptibility to bark beetle infestations and wildfires. Burn scars alter runoff behavior dramatically. Severe fires remove vegetation, and hydrophobic soils can produce flashier runoff events, accelerating erosion while reducing long-term infiltration stability. Sediment pulses from burned watersheds can then enter reservoirs, reducing storage capacity over time through sedimentation. This process occurs naturally in all reservoir systems, but becomes increasingly problematic when water storage margins are already critically low. Climate models suggest the basin may continue trending toward warmer and drier conditions through coming decades, though uncertainty remains regarding precipitation variability. The central issue is not simply whether rainfall decreases, but whether evaporation and temperature increases outpace any gains in moisture input. The Colorado River already demonstrates the mathematics of imbalance. Experts note that water use plus evaporative losses now exceed the river's actual annual flow by substantial margins. Reservoir depletion temporarily masks this imbalance, but reservoirs cannot compensate indefinitely. The geological history of the American Southwest contains warnings about such transitions. During past climatic shifts, river systems reorganized drainage patterns, lake levels fluctuated dramatically, and ecosystems transformed across entire regions. Human infrastructure, however, is built around assumptions of relative stability. Modern cities throughout the Southwest expanded during one of the wettest intervals in the basin's long-term record. Las Vegas, Phoenix, Los Angeles, San Diego, Tucson, and many agricultural districts became dependent on flows sustained partly by 20th century climatic luck. Population growth continued even as hydrologic conditions deteriorated. The river now supports roughly 40 million people and millions of acres of farmland. Agriculture plays a particularly important role in basin hydrology because irrigation fundamentally alters water movement across landscapes. Large portions of diverted river water evaporate from fields or infiltrate soils rather than returning efficiently to the river system. Certain crops grown in arid climates require enormous volumes of water due to high evaporative demand. From a physical standpoint, the basin increasingly resembles an overdrawn account where withdrawals consistently exceed deposits. The phrase megadrought has become common in scientific literature describing the western United States. Tree ring evidence suggests the current drought period ranks among the most severe in at least 1,200 years. What distinguishes the modern episode is the contribution of anthropogenic warming. Higher temperatures intensify drought impacts even when precipitation deficits alone might not appear extraordinary. In other words, heat amplifies dryness. This amplification emerges through several mechanisms simultaneously. Snow melts earlier, soils dry faster, plants transpire more water, reservoirs evaporate more rapidly, atmospheric moisture demand increases. The entire hydrologic cycle accelerates while becoming less efficient at retaining accessible freshwater. One of the most concerning aspects of the Colorado River crisis involves feedback loops. As reservoirs shrink, political pressure to extract remaining water intensifies. Emergency conservation measures may help temporarily, but if climatic conditions continue deteriorating, the system enters progressively narrower operational margins. Federal proposals now contemplate major water reductions across lower basin states. Some scenarios involve cuts measured in millions of acre-feet annually, yet even these negotiations ultimately confront geological reality. Laws cannot create runoff. Political agreements cannot manufacture snowpack. The river is constrained by the energy balance of the atmosphere, the elevation of mountains, the permeability of rocks, and the physics of evaporation. The future of the Colorado River may depend partly on whether the basin can transition toward a new hydrologic equilibrium before reservoir collapse thresholds are reached. Conservation alone may not fully compensate for declining flows if warming continues intensifying. Desalination projects along the Pacific coast have emerged as one proposed supplemental solution. Some western states are exploring water exchange arrangements involving desalinated seawater, but desalination introduces its own energetic and environmental constraints. It is not a geological replacement for snow-fed continental river systems. The deeper issue remains planetary energy imbalance. As greenhouse gases trap more heat, the western hydrologic cycle reorganizes around warmer baseline conditions. Mountain snowpack, once the basin's natural water battery, becomes less reliable. The Colorado River itself has survived tectonic upheaval, volcanic activity, canyon incision, glacial interglacial cycles, and ancient droughts spanning centuries. Geologically speaking, the river will continue in some form long after modern political systems change. But the version of the river that 20th century civilization depended upon may not survive intact. That distinction matters. Rivers are not static pipes carrying guaranteed volumes of water. They are expressions of climate interacting with topography across time. The Colorado River exists because winter storms, mountain elevations, erosion gradients, and seasonal melt cycles historically aligned within a particular climatic envelope. Human civilization expanded around that envelope as though it were permanent. Now, the boundaries are shifting. Scientists monitoring reservoir elevations during 2026 increasingly describe the system in terms once reserved for worst-case modeling scenarios. Emergency releases from upstream reservoirs, collapsing snowpack forecasts, declining hydropower reliability, and legal deadlock among basin states all point toward a system approaching physical limits. Yet the most important story may not be the reservoirs themselves. It may be the mountains. If warming continues reducing Rocky Mountain snow accumulation, then the fundamental engine powering the Colorado River weakens regardless of downstream engineering. Reservoirs can buffer variability temporarily, but they cannot substitute indefinitely for missing inflow. The river's fate therefore depends on a chain of geological and climatic processes stretching from Pacific Ocean evaporation to alpine snowfall to canyon runoff. A disturbance anywhere along that chain propagates downstream. The question is no longer whether the basin is stressed. The question is whether the Colorado River system can stabilize before critical thresholds trigger irreversible operational failures. Can reservoirs remain functional if runoff efficiency keeps falling? Can hydropower survive declining lake elevations? Can sediment-starved channels maintain ecological integrity? Can groundwater systems recover after decades of depletion? Can a river allocated beyond its natural average flow continue supporting modern demand under a hotter climate? Those questions define the real meaning of the Colorado River crisis. Not merely a drought, not merely politics, but a confrontation between human expectations and the physical limits imposed by geology, climate, and hydrology themselves. Perhaps the most unsettling aspect of the Colorado River crisis is that the basin may already be crossing invisible thresholds that cannot easily be reversed. Hydrologists increasingly warn that long-term warming could push parts of the Southwest into a permanently altered hydrological state, where even unusually wet years fail to fully restore reservoirs. This is because the system no longer responds the way it once did. In colder decades, heavy snowfall translated efficiently into spring runoff. In today's warmer climate, much of that water disappears before reaching the main river channels. Snow sublimates directly into vapor, soils absorb meltwater like dry sponges, and forests stressed by heat consume larger amounts of moisture through transpiration. There's also growing concern about atmospheric drying across the basin. Warm air acts like a stronger vacuum for water vapor, pulling moisture from lakes, rivers, vegetation, and ground surfaces at accelerated rates. Scientists sometimes describe this as a rising evaporative demand problem rather than simply reduced precipitation. Even if storms occasionally return in force, the atmosphere itself now removes water faster than the landscape can retain it. The Colorado River is therefore becoming a real-time experiment in planetary warming. What happens here may foreshadow the future behavior of other snow-fed river systems across the world, from the Andes to the Himalayas, where billions of people depend on meltwater borne high in mountain ranges.